Hi everybody, my name is Maxime Chevalier-Boisvert. I work at Shopify as part of the Ruby and Rails infrastructure team, and today I'm here to tell you about ZJIT, a project to build a next-generation Ruby JIT compiler. So in this talk, I'll give a short history of YJIT. I'll talk a little bit about why we want to build a new JIT, the limitations of YJIT, two key design changes that we want to make with this new compiler, two new major features that we want to include in ZJIT, the current status of the project, and what to expect for Ruby 3.5. So first, a short and incomplete history of YJIT. I joined Shopify in 2020 and formed a team with two other engineers, and we built what was first called MicroJIT, which was kind of a prototype JIT compiler. We had a time budget of 3 months. We got up to 10% speed up on smaller benchmarks with this prototype, and we managed to outperform vanilla Ruby by 1% on the liquid template rendering benchmark. But unfortunately, this prototype underperformed on Railsbench because it spent too much time entering and leaving JIT code. But still, Ruby and Rails infrastructure was kind enough to give us the green light to work on a real JIT. And this time we had 9 months to deliver double-digit speedups on opcarrot, single-digit speedups on Railsbench, and low warm-up time. And we ended up having better success than expected. YJIT worked even better than the objectives we had initially set. We got some clear double-digit speedups on realistic benchmarks, sometimes over 20%. And we were able to run all of Shopify's storefront render infrastructure and serve real web requests. I first presented YJIT at RubyKaigi Takeout 2021 with some great performance numbers. And following this, Takashi Kokobun made an invitation for us to open a ticket to upstream YJIT into CRuby. This was very well received. Matt saw it and approved it. And shortly after, it was merged. And so YJIT went on to be part of Ruby 3.1. Over the years, we've had better and better performance numbers, particularly on opcarrot, which is the most important Ruby benchmark. With Ruby 3.3, we managed to reach a 3x speedup over the Ruby 2.7 interpreter. And in all of my talks, I like to have these slides with people who have contributed to YJIT, just to remind people that it's a team effort, it's not just me. And the team has kind of had many people contributing over the years. Eventually, Takashi Kokobun joined us and made some amazing contributions to YJIT as well. And the team had more and more contributors at different points in time. And in 2025, one slide doesn't even suffice. We have new amazing contributors helping us make our Ruby better. We've also seen many deployments of YJIT. The first big deployment was at Shopify on our storefront render infrastructure. Initially, we had something like 10% end-to-end speedup. So this is like the total time that it takes to do the web request, including database and I/O. And now those speedups are closer to 20%. YJIT's also been deployed at Mastodon, the social, at Discourse, and at many other tech companies over the years, with people reporting excellent results, sometimes all the way up to 30%. And even today in 2025, there are still people enabling YJIT and getting great performance results. But I would say for me, something clicked the last time I was here in Okinawa for RubyKaigi 2024. Someone from Zendesk came to talk to me, and they said, we just enabled YJIT at Zendesk right before leaving for RubyKaigi, and we're getting 20% improvements just by flipping a switch. This is amazing, thank you. But the thing that struck me is that they said they were running Ruby 3.3.1. And at Shopify, we were also running the latest Ruby. I knew GitHub was also running the latest Ruby because they had deployed YJIT. And this made me go kind of like, wow, when I joined Shopify, I remember people being several Ruby versions behind. And we were kind of struggling to get people to upgrade to the latest Ruby. But now all of a sudden, it's like, if you can tell people, hey, if you get the latest Ruby, your software is going to run 15% faster, you don't have to ask twice. In fact, maybe you don't even have to ask at all. So as of today, we track the performance of YJIT on speed.yjit.org, and we've got some pretty great results on benchmarks. We can see, like, on the liquid render benchmark, which is actually YJIT 3.4, we get about 2.8x speed up over the interpreter. On average, we get about 2x across our benchmarks. These are all benchmarks that are meant to be like representative of like real world workloads that people would use Ruby for, primarily web workloads. Rails bench were over 2x faster. And there's something like a 6 to 8% performance difference between YJIT 3.36 and the latest YJIT development version. So congratulations, we did it. We transformed the Ruby performance landscape, which is great. But there's always a but. I feel like we're kind of hitting a plateau with the performance of YJIT, to be honest. And what I mean by that is that the first version of YJIT had 20% speed ups over the interpreter. And then the next version after that, we had like a 15% speed up on top of that 20% speed up. And then with YJIT 3.4, we're getting like maybe a 6 or 8% speed up, but it's not uniformly distributed. There are some benchmarks where it can be like 20%, but there are some benchmarks where we're not really seeing that much of a speed up. Timey reported they upgraded from YJIT 3.3 to YJIT 3.4, and they got about the same performance with YJIT 3.4 as with 3.3. So, well, maybe that's not entirely our fault because, web apps have database requests, and obviously, YJIT cannot make your database requests run any faster. It just can't do that because it's not a database JIT. But still, there's also this micro benchmark that went around Twitter, which is like 1 billion nested loop iterations. And well, this is actually Ruby without YJIT. With YJIT, it's about the same speed as PHP, which, it's nice. Like with YJIT, we can double the speed of this micro benchmark, and we can say like, haha, take that Python. But but if you compare, even YJIT to the JavaScript JITs, like even if Ruby can do it in 10 seconds, like it's like an order of magnitude difference. And this is what the micro benchmark looks like. It's like 2 nested loops. It does something with an array. So obviously you can look at this benchmark and you could say, well, that's nothing like Rails. It's not a real benchmark. Like you don't run this in production, obviously. This micro benchmark is not at all representative. But at the same time, if this benchmark is so basic, why do we perform so poorly? Because obviously, like, it's a very simple benchmark. Like, we should be able to run this faster, and probably your Rails application has loops inside of it too. So if we could speed up code like this, then probably we could make all Ruby code run faster. So we could do better. And I really want us to do better. Like, I'm sorry we couldn't make those micro benchmarks run faster. So I asked ChatGPT how to say sorry in Japan, and it said. Just kidding. So obviously, JavaScript is more than 10x faster on this micro benchmark. Why couldn't Ruby match JavaScript speed on those simple loops? We should make that happen. That's not possible everywhere, right? It's like even if we make a better Ruby JIT, we can't guarantee a 10x speed up on everything because, for example, like how much faster can you make string concatenation with a JIT? Like I think actually you can make it run faster, but you can't make memcopy run 10x faster. But still, what if we could double YJIT's peak performance? Like there's many obvious optimizations that we're currently not doing, and those speedups should and would translate into real workloads too, because real workloads use loops as well. I think performance is a feature. Like I've already talked about how people were so motivated to upgrade to Ruby 3.3 for performance improvements. History tells us we can never have enough compute. I also think to some extent, like this is important because it's a matter of survival. Like if you want Ruby to survive long term, performance definitely matters. Like Ruby is a cool language. It's a great language. But if your language is not fast, I think it will eventually die just because of the relentless march of progress. Like there's a relentless push to always optimize performance, always reduce costs. And in a world where single core performance is also hitting a plateau, we need to remove all bottlenecks. And so let's not let Ruby ever be a bottleneck. Let's try to build a truly world-class Ruby JIT. So interesting ZJIT. For the last 2.5 months, the YJIT team has been working on ZJIT. It's not just a better YJIT, it's a prototype of a next generation Ruby JIT that incorporates the learnings from the last 4.5 years of YJIT works, all of the hundreds of experiments that we've done, both on benchmarks and also using production data, all of the experience that the YJIT team has. I have tremendous confidence in the YJIT and ZJIT team. And this JIT is going to be designed to be more maintainable and extensible, hopefully a JIT that could last for maybe like the next 20+ years of CRuby, so that we don't need to keep rewriting better JITs. Like build something that we can build and maintain and extend for the long term. So first, the most important question I get asked, how do you pronounce it? Some people say ZJIT. Personally, I prefer ZJIT because it sounds more like ZJIT, So let's talk about ZJIT core architecture. YJIT architecture, YJIT directly compiles the YARV bytecode into machine code. It's a relatively simple architecture, which was good for us to get something working quickly. Like I said earlier, originally YJIT was built with a very limited time budget, like 3 people, 9 months. We grew YJIT incrementally over time. We added a cross-platform assembler, which allowed us to support both x86 64 and ARM 64, so that makes it possible for YJIT to run on new MacBook M1, M2, M3 laptops, for example. We've added some basic inlining for very small methods. Like if you have a method that returns a constant, we can inline that. We added custom code gen for core C methods. We added context metadata compression to make it use less memory. But we're getting to a point, I think, where we're hitting the limits of YJIT's current architecture. It's getting difficult maybe to extend and improve this architecture, which is why I think we need to make some changes. Engineering is all about trade-offs, finding the best trade-off given different constraints. So it's kind of like the classic, fast, good, and cheap, pick 2. YJIT was based on lazy basic block versioning, which is a JIT architecture based on my PhD research with the goal of like building a JIT with good performance quickly. That was like the aim of my research. But for ZJIT, I want us to build a method-based JIT compiler that's not going to be based on lazy basic block versioning, and this is a deliberate choice. There's kind of like a question like, could we design a more advanced JIT based on lazy basic block versioning? Like, I have some ideas on maybe how we could do that, but that's kind of a research project, like in a way, right? It's like lazy basic block versioning came from my PhD research, but if we wanted to try to extend like this kind of like exotic compiler architecture into something more, we'd be taking some amount of risks because there are many unknowns. And I feel like I don't want to impose that risk on the team and Shopify and the Ruby community because Ruby is not my personal research project. So for ZJIT, I want us to make a safer bet and go with a traditional established way to build a JIT, an architecture that has a known design, which helps us to minimize risk and means that we have a very high likelihood of success. The reason we think we have a very high likelihood of success is because most JITs are method-based JITs, and we know it works. There's no reason why it wouldn't work. So ZJIT is going to have a design that I want the design to be more standard, like something you would read about in a compiler textbook, with more standard foundations, which doesn't mean that we can't build cool stuff on top. But method-based JITs can make for an architecture that's very modular and extensible, with different parts that we can swap in and out as we improve the design. But yeah, the benefits would be low risks because it's proven design that we know works. And I think this would also make maybe ZJIT more accessible to newcomers. like a problem that we have with YJIT right now, I think, is that like the knowledge of how YJIT works exists mostly at Shopify and GitHub, but we've had very few commits from Ruby core contributors. So I think if we had a JIT that had a more standard design, it might make it easier, for example, for the rest of the Ruby community to also participate in the development of this JIT, which is good for Ruby long term. Standard doesn't have to mean boring. Like I think once we have stable foundations, we can do many cool experiments. My PhD advisor, Mark Philly, and his PhD student, Olivier Melançon, published about static basic block versioning, which is kind of an offshoot of my PhD work. And I think this could be done in a method-based JIT context later if we want to, but it can be self-contained and a very low-risk experiment as opposed to like part of the core foundation of the JIT compiler itself. The next significant design change for ZJIT is it's going to have its own intermediate representation. So YJIT compiles YARV bytecode directly into machine code, which makes for a very simple architecture. But this is not at all optimal for a JIT compiler. YARV bytecode is designed for the MRI interpreter. If you want to maximize the performance of an interpreter, basically like you want bigger instructions. So you want to minimize the dispatch overhead in your interpreter loops, right? So you don't want lots of tiny instructions. You want bigger instructions that do more work. You also want those bigger instructions because you can give your C compiler, assuming it's written in C, a bigger chunks of code to optimize all at once, right? So bigger instructions means it's better for the interpreter. So you end up with like a very CISC design, so to speak. But this is kind of the opposite of what you want for a JIT compiler. JIT compilers typically have what's called an intermediate representation. This is like the way the compiler internally represents code. It's the compiler's internal language. And what you want from a JIT IR is to decompose a complex semantics into like small composable primitives that enable kind of like algebraic operations and transformations on code. You want those instructions to have as little internal control for as possible because that makes the code easier to reason about and to optimize. So you want something that's more like a minimalistic RISC-like instruction set. If any of you have seen this amazing documentary, the key takeaway was that RISC is good. So ZJIT is going to have an SSA-based IR. SSA means a static single assignment. This is something I learned about in university in a compiler class. It was originally developed at IBM in the 1980s, and you can read about it in many compiler textbooks. It's basically like the most widely used compiler IR, both for JIT compilers and also for many ahead-of-time compilers. It's kind of a de facto standard that's used by LLVM and GCC, and it's proven to be flexible and robust. So again, like I talked about having a standard design, this also goes strongly in that direction. This is the original paper from Popple, 1988, introducing the formalism of the SSA IR. So just to show you what that might look like, so here's a very small example of a recursive factorial microbenchmark. The YARV bytecode for this microbenchmark looks something like this. And then in terms of this is a dump of ZJIT's IR. The IR is divided into blocks, not to be confused with basic block versioning, but just like control flow graph blocks. And it has instructions like fixed num LE is fixed num less than, so this is checking if V5 is less than V2. We have like if false, this is a branching instruction, like basically if V8 is false, jump to BB1. Fixed num sub would be a fixed num subtraction. Send without block direct is a recursive send where like the factorial calls itself. And also something you can see is like all of the instructions are annotated with type information. We also have patch points, which allow us to de-optimize code. Like Okuben talked a little bit about this sort of thing in his talk yesterday. And we have guards that basically here, if V12 is not a fixed num, exits to the interpreter. Now I want to talk a little bit about some key features that are going to be part of ZJIT. So CRuby, one of the things that's challenging about CRuby and about YJIT is that method calls are very expensive because they have many corner cases that they need to handle. The Ruby VM also has two stacks. It has a VM stack or value stack and a CFP stack. So there's lots of work involved in like setting up a complex CFP object. YJIT can make that run faster. Like actually, YJIT can make micro benchmarks that are basically only calls run like 8 to 12x faster than Ruby. But this is still probably like half of like the peak theoretical throughput of what's possible. And also we have an issue where like we're generating tons of machine code, and even though we can make this run really fast on micro benchmarks, like massive code size is not good for your instruction cache. It's not good for instruction decoding. Like it slows things down elsewhere. So we need to do something about this. Like other languages like JavaScript have much faster calls, so Ruby should too. So in ZJIT, we want to have what we call fast JIT to JIT calls. YJIT calls are suboptimal for multiple reasons. One is they use the JMP, like the jump instructions, and they use a very long code sequence to set up the VM and CFP stacks. But to get the maximum performance, we want to use the CPU's call and return instructions because those are better optimized. And we want to directly use the C stack to make those calls as opposed to the VM and CFP stacks. So we're designing ZJIT directly to use the C stack for JIT to JIT calls. So that means like when a JIT function calls another JIT function, it's going to use the C stack. But when it needs to exit to the interpreter, it needs to pay a little bit of a performance penalty to do this side exit. So again, it's like engineering is all about trade-offs, right? Like the Shinkansen can go really, really fast, but it can't make sharp turns. But I think we can all agree that high-speed trains is still a very good idea. So we have some early experimental results. Takashi Kokubun got fast JIT to JIT calls working in ZJIT using call and return instructions as of just a few days ago. And we got the recursive Fibonacci benchmark working. This is not how you should compute Fibonacci numbers. It's just like an exercise to test the performance of method calls in ZJIT. So this is what the micro benchmark looks like. And as you can see here, YJIT is about 10 times faster than the interpreter on this micro benchmark. And then ZJIT is like another 60% faster. I think we can even make it run faster than this. We might be able to be like twice as fast as YJIT eventually. So this is very, very encouraging. The second key new feature of ZJIT, JIT compilation is kind of a balancing act. Your JIT compiler has to juggle multiple trade-offs. One is the performance of generated code. The other one is the warm-up time. Then there's the memory overhead, how much memory the JIT compiler uses. So your JIT compiler runs at the same time as your program, which means the JIT compiler is kind of like competing with the running program for resources. So JIT compilers effectively operate in like a resource-constrained environment where you need to minimize the amount of memory and CPU time that your JIT uses because otherwise you're taking those resources away from the running program. But by optimizing to reduce memory and CPU usage, you're kind of limiting how effective your JIT compiler can be. And then we have another problem, like Shopify has has a certain number of servers, bazillions of servers running in large data centers, and we're redeploying code sometimes multiple times a day on these 3 bazillion servers. But at the same time, it's like when you're redeploying code in production, probably 99.99% of the code that you're deploying has not changed. You know, it's like maybe someone made a pull request and they changed like the variable food to be named bar. And so it's like, okay, let's redeploy all of this code on lots of servers and like, okay, like recompile everything on all of those servers, which just seems really inefficient, right? So what if we could save and reuse compilation work? What if we could serialize and persist machine code? If we could do that, when we could maybe hit the ground running and warm up much faster than we could with YJIT, which also means potentially we could spend more time compiling code and enable higher optimization levels. Because if you can JIT once and reuse that work many, many times later, then it becomes worthwhile to spend more time JITting in the first place. So there's some challenges here, like we need to save not just code, but also metadata. We need to save the optimization information. And also compiled code can contain pointers to ICX or Ruby strings. So we need kind of like a mini linker to handle these things. So it's not trivial, but it is possible. There are JITs that do this already. And if we could make this work in ZJIT, this could again be kind of a game changer. So what is the current status of ZJIT? Well, we started development just like 2.5 months ago. We've already implemented our custom SSA IR. We have comparisons and fixed norm operations working, control flow working, fast JIT-to-JIT calls, constant and type propagation, dead code elimination. After 2.5 months, we can run simple micro benchmarks like the ones I've just showed you. And we're faster than the interpreter and even faster than YJIT on some of those micro benchmarks. But obviously, like, this is still very early innings at this point. We've also opened a proposal to upstream ZJIT to make developments easier. We've discussed this with the Ruby core members, which were very receptive. Matt has expressed that he has complete confidence in the ZJIT team, and so he's in favor of upstreaming. So thank you, Matt, for the vote of confidence. Upstreaming should probably happen in the next 3 to 5 weeks would be my expectation. We have a command line option to enable ZJIT as with YJIT, so ruby-ZJIT. If you're interested, you should keep in mind that right now ZJIT is not at all in a usable state for production or any like real workloads. I would expect that it's going to become more usable around like the second half of this year, because right now we're just like in the process of laying down the foundations, but we're making really rapid progress. So what to expect for Ruby 3.5? The plan is for YJIT to still be available in Ruby 3.5 because we want to guarantee that Ruby 3.5 ships with a working JIT. So we're not going to remove YJIT until we're confident that ZJIT is faster and just as stable. But for now, it's like we're putting YJIT into maintenance mode so that we can dedicate all of our mental energy and all of the resources that we have to building this much better, much more forward-looking JIT. When Ruby 3.5 comes out, you may or may not need to run configure with enable ZJIT to build it. That's going to depend on the maturity level of ZJIT around the time of the Ruby 3.5 release. So we're going to make that call closer to the end of the year. We believe it should be possible to have both YJIT and ZJIT in the same binary to be determined, but we think it's possible, which means like for Ruby 3.5, you should be able to toggle both like, ruby-ZJIT and ruby-YJIT. So basically, like, you shouldn't need to change anything in your production deployment, but you should also be able to try ZJIT, kind of like in a beta state maybe. We're hoping to match YJIT's performance for this release. I think it's very likely my expectation is that we're going to start to beat YJIT on more and more benchmarks as the year progresses, and hopefully, wipe the floor at the end of the year. But obviously, it's like we can't necessarily like guarantee the pace at which things are going to go. So beating YJIT on larger, more realistic benchmarks would take a little bit of time. The next steps, so fast JIT calls are already like working thanks to Kokubun. After that, we're going to add the ability to side exit to the interpreter in the next few weeks, which Kokubun explained in his talk. That's going to enable us to more extensively test ZJIT, run the Ruby test suites, and also to run benchmarks on speed.yjit.org. So what I want is for like the second half of this year, I'd like to start tracking, ZJIT is outperforming YJIT on this many benchmarks out of this many, kind of like gamify the thing a little bit for the team, make it fun. We're going to gradually grow the feature set of like what ZJIT supports, which is a lot of work, but we'll get through it. And we're going to measure and optimize the compilation speed to make sure that it runs fast and tune the compiler. So that's it for me. Thank you for listening. If you want to learn more, if you want to follow our work, you can go subscribe to the Rails at Scale blog or check it periodically. You can also come talk to us after this talk, and I should also know that Shopify's Ruby on Rails infrastructure is hiring. We're hiring compiler experts for ZJIT. We're hiring C and Rust systems programmers, as well as world-class Ruby and Rails experts. If you're interested in working as part of Ruby and Rails infrastructure, you can use our QR code to apply if you're interested. And yeah, that's it for me. Thank you.